Okay, 1.6, beyond the unit circle. The main idea behind this section is we don't have to always be doing this stuff on the unit circle. The hypotenuse doesn't have to be 1, right? We can still go back to those formulas where instead of just sine being y and cosine being x, we actually have to divide by a radius that's not 1. So that's what we're keeping in mind in this section. We don't want to get too used to that unit circle and not having to divide by the hypotenuse that we forget to divide by the hypotenuse. So, suppose theta is an angle in standard position and Q, point xy, is a point on the terminal side of theta that lies on a circle of radius r centered at the origin. So we still are considering a circle with the radius, and we have our x and y values, so we still have a right triangle, but instead of a hypotenuse or radius of 1, the radius can be whatever, right? So then our formulas are a little more complicated because we have to have that r value considered in there. All right, well, sometimes we don't even know what r is. All we know is what x and y are. That's what this is getting at, is what if all we know is x and y? Well, x and y are the sides of a right triangle, and r can be found using Pythagorean theorem, correct? So sine, therefore, instead of just being y, can be what y over r. Or, if needed, to find r, it can be y over the square root of x squared plus y squared. Does that make sense? So what is cosine? It's the same idea. Yeah, so x divided by the hypotenuse, which can be found by using Pythagorean theorem. Now the cool thing about tangent, we still got that one. Still y over x. Because no r radius is involved, so all that matters is x and y. Trying to think. I had another thought pop in my head, but now I don't remember. Oh, I don't know if I've talked about this with tangent before. If I have, well, you can hear it again. Think back to linear equations and slopes. Slope is sometimes known as rise over run, or like the difference in y divided by the difference in x, right? So if we're going from the center, 0, 0, to a point, x, y, that would be a rise of y and a run of x, because it's going from 0, 0. Guess what tangent is? Tangent is slope. So if you have your terminal side of your angle, tangent is literally giving you the slope of that terminal side. So it's just kind of an interesting little tidbit, a little correlation. When tangent is negative, that means your line is sloping negative, if you remember this stuff from algebra. When tangent is positive, that means your slope is slanting, your line is slanting the positive direction, right? So anyway, there you have it. Okay, cosecant. So cosecant is the reciprocal of sine, so we can call that r over y, or we can find that using Pythagorean theorem. So we would have x squared plus y squared over y, reciprocal of the sine, right? And then secant can be found with r over x, so square root of x squared plus y squared over x. And then cotangent, of course, is just the reciprocal of tangent, so x over y. So now, as long as you have a point on the terminal side of your angle, you can find any of your ratios using these formulas. And it's really just opposite over hypotenuse, adjacent over hypotenuse, or opposite over adjacent, or, you know, just those basic definitions we've learned, but in terms of x and y and r, but r is also in terms of x and y. So with x and y, we can find everything. Let's look at some examples. Are we good? Okay, suppose that the terminal side of angle theta, when plotted in standard position, contains the point Q 4, -2. So I'm going to plot that point. because I like having my visual reference. It's always nice to know what quadrant we're in and have a triangle to draw out, right? So let me grab binder. I just change that to red. Oh, I changed the color of that line. That's not what I was going to do. Okay, line. Turn it red. Draw my triangle. There's my triangle. There's my point XY. So that means that this side has a distance of 4 and this side is a distance of 2, but it's down 2, which is important. So this is R. Maybe we should go ahead and find R. What do you think? Would that be helpful to just find R since R is in so many of our formulas? If we just had that to begin with, then we wouldn't have to, like, you know, just find it once, basically, right? So let's go ahead and do R. X squared plus Y squared. So that'll be 4 squared and 2 squared. So square root of 16 plus 4, which is the square root of 20, which is, if you remember how to simplify this, square root of 4 times 5. So square root of 4 is 2. And we have square root of 5 left over inside. You guys remember how to simplify radicals like that? Does that sound familiar? Do we need a little review? A little review. Okay. All right, we'll come back to that in just a second. So maybe just trust me on it for a second here while we find all of our answers. Okay, so sine of this angle theta is our opposite side, the y value, divided by the hypotenuse, which I just found, is 2 square root 5. Now, typically, you should always reduce if you can. So can we reduce this one? Yeah, -1 over square root of 5. You could even rationalize it if you want to, but you don't have to. You can. So if you rationalize it, it would be square root of 5 over 5. Okay, what about cosine? Perfect. Yeah, and then we can rationalize, or I mean, we can simplify it. So 2 over square root of 5. Okay, or we can rationalize it if we want. 2 square root of 5 over 5. All right, 2 down, 4 to go. Okay, tangents. It's just going to be y over x, so -1/2. So that means we should be able to do these others rather quickly. Cotangent is -2. Cosecant, we just need to take this unrationalized sign and do the reciprocal of that, so that'll just be the negative square root of 5. And then, that's weird, that theta going. And then secant is just going to be the reciprocal of 2 over square root of 5, so square root of 5 over 2. So see why you may not even want to rationalize them, because if you don't rationalize them, they're much easier to flip over for your other ratios, and then those are actually rationalized. But you still need to understand this process, so it doesn't hurt to do that. Okay, I want you guys to try example 2 on your own. All right, hopefully you were able to do example 2 on your own. Here's the answers we got. We drew the triangle. We got a 3, 4, 5 triangle. So when we do Pythagorean theorem, we get the hypotenuse is 5. So then from that, we found all of our ratios. I almost forgot to put the negative here. And I know in a lot of these, I've put the negative where it's in front of a specific number. That's not important. As long as the numerator or the denominator is negative, that whole fraction is negative. Because if they were both negative, then a negative divided by a negative would be a positive. And we wouldn't leave it negative. So just, it doesn't really matter where you put the negative. And then going back to what I mentioned earlier with simplifying radicals. So here's a little bit better version of what we did down here. So up here, we took our x value squared, our y value squared, added them together and got the square root of 20. Well, 20 is not a perfect square, so then we figure out if there's any perfect squares that divide into 20. Hopefully you could think of 4, the number 4 does, and 4 is a perfect square. So I divided that into separate square roots, and the square root of 4 is 2. So the resulting simplified radical is 2 times the square root of 5, which has the same equivalent value as the square root of 20.